Hello everyone, welcome to the lecture number 29 of this NPTEL lecture series on charging infrastructure, and in this lecture we will continue our discussion on the closed loop control of three-phase AC to DC converter. So let us recap some of the things we have discussed. We have started with our control objective, which was to control the output voltage or regulate the output voltage at a desired value, and along with that maintaining the unity power factor operation when we are drawing current from the grid. So to do that, we have, for balanced three-phase operation, we understood that the current which is drawn from the grid as well as three-phase voltages are not independent of each other, they are dependent on each other. That means once we are changing one of the phase currents, other phase currents are also getting impacted because of the balanced three-phase operation. So to do that, what we did was we have defined the two reference frame. One is alpha beta reference frame, which is a stationary reference frame where there is a voltage space vector which is rotating in a space with angular speed equal to 2 pi fs, and the alpha and beta frame are stationary in the space. And because of that, since alpha and beta are 90-degree apart from each other, the component of Vs space vector along the alpha axis and beta axis are independent of each other. That means whenever you are changing the alpha component, the beta component is not getting impacted, and whenever you are changing the beta component, alpha component is not getting impacted, and that is when we can achieve the independent control of the two alpha beta components. That is a stationary reference frame. Similarly, on the similar line, so we then define another reference frame which is called as a DQ reference frame, and that is also called as a synchronous rotating reference frame or rotating reference frame, because we align our D axis in such a manner that the D axis is aligned along the rotating voltage space vector. That is when, by making sure the component of Vs space vector along the Q axis is equals to 0, that is when we can ensure that D axis is completely aligned along the voltage space vector. And we then define the current space vector, and if we ensure that ISQ component is equals to 0, that is when we ensure that the IS space vector is perfectly aligned along the D axis, and as the D axis is aligned along the voltage space vector Vs, that is when we can ensure that my IS space vector and Vs space vector are completely aligned, and that is when we can say that in all the three phases we have the unity power factor operation. Then we define our DQ axis model, where we saw there are some cross coupling terms and some constant term that we understood. We have removed those terms by putting the feed forward terms, and that is when we have made the two independent loops. This is my Q axis, or you can say the Q axis loop, and this is the D axis loop. And since we know that we are actually aligning our IS space vector along the Vs space vector, that is we are doing it by making sure my ISQ reference is equals to 0, and that is when we can ensure we have the unity power factor operation of this three-phase AC-DC converter. Since we know that our prime objective is to regulate the output voltage depending upon whatever the reference we have selected, and that if there is a mismatch in that, that will give the reference to the ISD component, because my ISQ component is 0, so it is only determining the ISD component, and because if the ISD component increases, that means the amount of current or the magnitude of current drawn from the source will either increase or decrease accordingly depending upon what is the output voltage of this converter we are having. Then after that, we get the converter voltage which will be applied by the three-phase inverter, and then we have two feed forward terms, and then finally we have defined the transfer function, converter transfer function, which applies the voltage across the series connection of L and RS, where RS is nothing but the equivalent series resistance of the inductance, and that will give my ISG. From that ISG we have evaluate the V0, and that we will feed for feedback via the voltage sensors, whose transfer function, because you know the voltage sensor also have their own bandwidth, their own gain is needed, because this voltage could be 400 volt, but this voltage you are setting up in the microcontroller, and that voltage could be either 3.3 or 1.8 or 2 volt depending upon the microcontroller you are using or the voltage level of the microcontroller. So that much gain you have to provide from the voltage sensor. So this is nothing but your transfer function of output voltage sensor. Nothing but this K2 is the gain, and denominator indicate the bandwidth of the sensor corresponds to 1 by T2, and for simplicity we assume that sensor has first order response. So that's why we have taken single order transfer function. Similarly for the ISD we are actually feeding it back into the loop, so that we are sending it through the current sensor, and that again current sensor we are just taking the gain to convert the actual current which is into the value of that current which is being put inside the microcontroller, and this is nothing but the transfer function of current sensor. And this is, assume that the current sensor has some bandwidth, that means beyond certain point there will not be any gain you will obtain from the sensor, and that we approximated with the single order transfer function. So we can get 1 by ST1 as the pole which will be representative of the dynamics of the current sensor. Similarly in the Q axis loop we have only the current loop, we do not have the voltage loop, because we want, ideally we want our ISQ reference to be 0, then only we can ensure our IS space vector is aligned along the D axis, which is aligned along the supply voltage space vector, and that is when we can ensure that we are actually drawing unity power factor current from the source. Now let us start understanding how we can find out this particular controller, how we can find out this controller parameters. So let us try to find out how we can obtain this controller and how the controller looks like, and how we can calculate this K value, this current controller and voltage controller, and what are the guidelines to do that. Let us calculate that, and then we will see overall how we can define our this closed loop control, and let us derive our closed loop control. Now let us first just take the current loop where we have ISD reference coming in and we have ISD feedback coming in, and we have a current controller. So here we have just taken the current loop. Okay, just the, if we look into only this loop, and this loop is nearly same, because the feed forward term will not introduce any dynamics. They are just constant values, either increasing or decreasing the V converter D and V converter Q values. So we can neglect them, and then we will have just this loop itself. So let us define the current controller, which is just a PI controller, which is nothing but Kp plus Ki by S. It is nothing but a standard PI controller. We will define this is for current control, so Kpc and KIC for the current loop, and that is when we will get, after this particular thing will be going to just the converter transfer function, which is nothing but G by just the half bridges transfer function, nothing but G by 1 plus STD, and that is actually going to 1 by SL plus RS transfer function, and that is nothing but my ISD which I am getting, and which will be feedback through the current sensor 1 K1 by ST1 feedback. Now in this particular case, let us define the closed loop transfer function of this. So let us define closed loop transfer function. So my closed loop transfer function will be my ISD which is going, I mean at the output, divided by my reference which I am setting up, is nothing but, let us say the current controller. Let us simplify the current controller. So current controller is nothing but Kpc plus Kic by S is nothing but, we can write Kpc, we can take it out, S plus Kic by Kpc divided by S. This we can just do it. So this is your current controller. So this current controller is having a 0 which is at Kic by Kpc, and that if I cancel out this 0 with this pole, that means we can also write 1 by SL plus RS to be, so this we can simplify it to 1 by L S plus RS by L is equals to, and that we can write further as 1 by L divided by S plus 1 by Ts, where Ts is equals to L by Rs. So in this particular current loop, one simple approach to obtain the current controller parameters is by cancelling out the pole associated with L and Rs with the 0 in the current controller, which will give us the condition to arrive at the current controller parameters. Thus we can write Kpc by Kic is nothing but equal to Ts. So this is one condition we are arrived at. I am cancelling out this pole with this 0. Now we can then further simplify this loop, and they can write from the closed loop transfer function in this loop, we can write down to be nothing but equal to G Kpc by L 1 plus S Td to S divided by this S comes from this one, and Kpc comes from this one. When we take it out, L is when we take it out this one from here, and 1 plus STD, this one divided by 1 plus G Kpc K1 by L 1 plus STD into 1 plus ST1, and this is S. Now so this, when we simplify, what we obtain is ideal S by ideal S reference is equals to G Kpc times 1 plus ST1 divided by S 1 plus STD multiplied by 1 plus ST1 L plus G Kpc K1, and let us define this as equation number 1. And in equation number 1, what we have is we have 1 plus STD, 1 plus ST1. So this I can write 1 plus S square Td T1 plus S Td plus T1. Now if you look very carefully, this Td is nothing but T switching by 2, which is T switching is nothing but the switching period or the carrier period, and my T1 corresponds to the bandwidth of current sensor, and this, if you look very carefully, this both the things, both the Td and T1 are very small quantity. For example, let us take switching frequency of 10 kilohertz, then the TSW is 100 microsecond and TD value is 50 microsecond, while the T1 generally will be taken at least 10 times smaller than the TSW value or switching cycle period. So it will be around 10 microsecond. So if we do the product of TD and T1, it will be very small, nearly 0.5 nanosecond. So we can write, and T1 are small quantities, are small values. So that's when we can say product of TD times T1 is very small, and it is nearly approximated to 0, we can say. So that means we can write 1 plus STD plus 1 plus ST1 is nothing but 1 plus S TD plus T1. I mean, this is the approximated value. And then from here what we can do is we can mention TD plus T1 is nothing but equal to T sigma, and that's when we can write is nothing but 1 plus STD times 1 plus ST1 is nothing but 1 plus ST sigma. Now from equation number 1, so from equation 1 we can write ISD of S divided by ISD reference of S to be equal to G Kpc 1 plus ST1 divided by S 1 plus S T sigma L plus G Kpc K1. So when we will rearrange this one, we will get the value as G Kpc 1 plus ST1 divided by SL plus S square T sigma L plus G Kpc K1. So this, when we rearrange, what we will get is S is equals to G, what we got, G Kpc 1 plus St1 divided by T sigma L is nothing but S square by S plus T sigma plus G Kpc K1 by T sigma L, and this we will define as equation number 2. This particular equation we can compare with standard second order transfer function, second order closed loop transfer function, which is nothing but, we can just say 2 zeta omega n, because if we look, the denominator of the standard second order transfer function is nothing but s square plus 2 zeta omega n s plus omega n square. That's denominator of we can say second order closed loop transfer function, CLTF. Closed loop transfer function, we can say CLTF. Now if we compare this and this denominator of equation number 2, what we gonna get is, we will get 2 zeta omega n is nothing but 1 by T sigma, and we will get omega n square nothing but equal to G Kpc K1 divided by T sigma L. Now this particular thing, if we keep zeta value to be 0.707, so we will get 2 by root 2 omega n to be equal to 1 by T sigma. So if we take the square on both sides, what we will get is omega n square is nothing but equal to 1 by 2 T sigma square. Further, from previous slide, what we can write down is that omega n square is nothing but equal to G Kpc K1 by T sigma L, and that when we simplify, what we will get is Kpc is nothing but equal to L by 2G K1 T sigma, and this is nothing but the current controller parameter, the proportional parameter what we will get. And this, if we see from this to this first condition, let us define this as condition number A, and let us define this equation as equation B. From A and B we can calculate the current controller parameters. That is how you can design your current controller. And since we can design our current controllers, we can able to do the inner ISG current loop control and the ISQ current loop control. Now after this, let us do the voltage control loop. To do this, from equation 2 we can just write ISD S by ISD reference to be equal to, we can write 1 plus ST1 divided by K1 multiplied by 2 T square S square plus 2 T sigma S plus 1. This is again, we got it putting B in equation 2, we will get this. So in this one we have a 0, and this 0 is at very high frequency, and in this denominator we have S square term. Now if we look very carefully, if we look our overall loop, in this loop we know that our outer voltage loop is slower as compared to the inner current loop, because then only whatever the changes it will occur, or it will ensure at the ISD reference, that ISD reference will be tracking that particular change. So thus we must ensure that our outer voltage loop is very slower as compared to the inner current loop. And generally the outer voltage loop is actually tracking down only the DC quantity, because output is just a DC quantity. So our outer voltage loop is very slow. So since our outer voltage loop is a slower loop, thus the dynamics due to 0 at 1 by T1 at S equal to 1 by T1 frequency, dynamics due to 0 and due to S square terms in denominator can be neglected. Why? Because let's say if we take this voltage loop is a slower loop, so frequency corresponding to that slower loop is very small, near to S equal to 0. So when we have frequency corresponds to dynamics closer to 0, that means S is close to 0 value, and the 0 in the numerator which is kept at 1 by T1 will have very negligible contribution towards the dynamics, as for smaller frequency the product of ST1 is very small, since both S and T1 values are very small quantities. Similarly, in the denominator, S square term can be neglected as S corresponds to a smaller value, and thus S square term will be further smaller value. So we can say that this particular part and this particular part can be neglected due to slower outer voltage loop. So thus our ISD and ISD reference, obviously these are closed loop transfer functions of this one, is nothing but it will boils down to 1 by K1 divided by 2 T sigma plus 1, and this is nothing but, let us define this as equation number 3, and this is nothing but the closed loop transfer function. If I write closed loop transfer function of inner current loop. Now let us see how the voltage controller parameters will be dependent. So let us try to write down the voltage loop. In the voltage loop, if we see, we have the V0 reference, we have V0 feedback. This is going to the voltage controller, which we define on the similar line as that of the current KIV by KPV. This is nothing but divided by S. Similar line as that of the current controller. This will be going to ISD reference, and this is ISD reference, and this is the overall transfer function which goes to 1 by K1 to T sigma S plus 1, and this finally gives me ISD, and then this particular ISD is going to a gain block called K, and that will be going to, you can say, I converter, and that I converter will be going through the capacitor having the impedance 1 by SC, which will give me my dynamics of the voltage controller. And then I have the outer voltage sensor, the transfer function corresponds to that will be taken feedback. Now in this one, in order to assign what could be the best possible KPV and KIV values, so what we can do is we can just define open loop transfer function, which will just say OLTF, and open loop transfer function, so we can say just V0 of S divided by V0 reference of S, this is OLTF, is nothing but, we'll just do the multiplication of that, so we'll get KPV times K times K2, this K2 will come over there, multiplied by S plus KIV by kPV divided by, if we do this thing, we will get S square C SC, and this S is there, and then we have K1 in the denominator, this K1, and then finally we have 1 plus 2 T sigma S, and then we have 1 plus ST2. Now again in this particular thing, let us define this as equation number 4. Let us define this one in 1 plus 2 T sigma S plus 1 plus ST2. If we see this one, again we do the same approximation, 1 plus 2 T sigma T2 S square plus 2 T sigma plus T2 S term. And if you look very carefully, this T sigma and T2 are small quantities, that's when the product of T sigma and T2 is nothing but equal to 0, or nothing but nearly equal to 0, or very small you can say. So thus we can say that 1 by 2 T sigma S 1 plus ST2, this is nothing but equal to 1 plus 2 T sigma plus T2 S, and then we can say 2 T sigma plus T2 is nothing but equal to T delta, and that we can just write down this one value to be 1 plus T delta S, and thus we can say, we can finally write our equation number 4 to be V naught of S by V naught reference of S OLTF, obviously open loop transfer function, is nothing but, if we see from this one, kPV K K2 into S plus KIV by kPV divided by to be S square C K1 1 plus ST delta. Now this is the open loop transfer function we can define. So in this, if you look very carefully, if you try to draw the Bode plot of this particular system, what just the gain plot if you try to draw, so what we have is gain in dB, if we do, and this is nothing but with respect to frequency. We see we have two poles at S equal to 0, that means we are having a very high values, and we are falling down, since we have two poles, we are falling down with minus 40 dB per decade. And then what we have is, we have one 0 and we have one pole. Now if we, if let's say the pole is placed at lower frequency as compared to the 0, then what will happen after this, it will fall down with minus 60 dB per decade, and then after 0 it will be falling by minus 40 dB per decade. And the other possibility could be, let's say we keep our 0 at this point, which is KIV by KPV, this 0 if we keep at this point, then after this we have minus 20 dB per decade the slope, and then after that slope what we will have is at 1 by T delta frequency, we have gain which is again falling with minus 40 dB per decade. Now at this point let us say this 0 dB line, and we have the 0 crossing at omega c. Now if we look very carefully, we know that if we have gain Bode plot, if it is crossing the 0 dB line with a slope of minus 20 dB per decade, then we can get a higher phase margin as compared to when it is falling with minus 40 dB per decade or minus 60 dB per decade. So we can say that in this one, if we cross the 0 dB line with slope of minus 20 dB per decade, then we can say then high phase margin can be achieved. That means we will get the stable closed loop operation. as compared to if we have minus 40 dB per decade or minus 60 dB per decade. It's primarily because if we look very carefully, we just plot the phase plot of this with frequency at this point, we are actually started our thing from minus 180 degree. So our phase plot will be having, you know, this is KIV by KPV and this is 1 by T delta. So our we are having minus 180 degree because we have s square term, and then at when we have a 0, so we have a good, we have some addition of phase and because of the 0 at this place, and then after that we will again fall back to minus 180 degree after, or we can say we have good this one 0, and then somewhere at this point, after this point we will fall to 1 minus 180 somewhere like this, not accurately drawn but somewhere like this. So this is the thing we can obtain, this is phase margin we can obtain, that means how much away from minus 180 degree we are when we plot the phase plot of open loop transfer function. This is phase plot of open loop transfer function, this is phase, and this is what we get the phase margin. So if we ensure this minus 20 dB per decade fall, then we can ensure we have a good phase margin, that means away, that means we can make sure the phase plot is that much away from minus 180 degree, and that is the same thing we will do it over here by keeping our 0 smaller than our pole. So one possibility could be we can put our this 0 crossing at the geometrical mean of this 0 and pole. This is one possibility, so that we can find some relationship, so where we can get KIV by KPV into T delta, and that this 0 cross, let us define this as some factor times 1 by T delta, and that if we try to find out, we will get A square T delta to be equal to KPV by KIV. Now this is one that means we can say KPV by KIV is nothing but A square T delta. Now this is one of this thing, so this, let us define this as C. So from C we can get this relationship. Now we know that at omega equal to omega C, my open loop transfer function V naught of S by V naught reference of S at omega equal to omega C to be equal to 1, the gain of this particular transfer function is equals to 1. So you can find out the gain over here, and then we can put this term in that particular gain. Finally we will get KPV to be equal to C K1 by K2 KAT delta. Now this is the value D, and from C and D we can calculate our voltage controller parameter. From C and D, voltage controller parameters can be obtained. So this is how we can ensure we will get the voltage controller parameters and current controller parameters. Still we don't know what is our value of K, so let us try to find what could be our value of K. To obtain K, what we can do? Now we can do simple thing, which is the power balance. So we can write our three phase power. The three phase power, since we have unity power factor operation, we get 3 times Vs peak Is peak by 2. Why we are getting by 2? Because Vs peak by root 2 and Is peak by root 2 is the RMS values, and V phase RMS, I phase RMS, 3 times of that we will get 3 phase power. Similarly, we can write 2 phase power to be VSD ISD plus VSQ ISQ, and we know that our VSQ is equals to 0 and ISQ is equals to 0, and we know that VSD is nothing but 3 by 2 times Vs peak and ISD is nothing but 3 by 2 times IS peak. So we can say that our two phase power is nothing but 9 by 4 Vs peak times Is peak. Let us this is defined as 1, this is defined as 2. From 1 and 2 we can say that the three phase power is nothing but 2 by 3 times two phase power. And we know that the three phase power is nothing but also equal to I converter what we are getting over here times our V naught value, and that is when we will get 2 by 3 VSD times ISD to be equal to I converter V naught, and that is nothing but my I converter is nothing but 2 by 3 VSD by V naught, and this times ISD, and this is nothing but equal to K. So from here we can say K is 2 by 3 VSD by V naught. Similarly, we can say our K1 value, which is the gain of the current sensor, maximum voltage of controller, or you can say that if it is 1 it is 1, if it is 3.3 it is 3.3, it all depends upon that, divided by 3 by 2 times maximum value of supply current. That means if Is peak is let's say 20 ampere, then it is 3 by 2 times of 20 ampere. Similarly, K2 we can say is nothing but maximum voltage of controller divided by output voltage. Let's say if here we have 400 volt and here we are giving 1 volt as a 1 volt corresponds to 400 volt, then our K2 value will be nothing but 1 by 400. Similarly for the case of current as well. This is what we can obtain the K1 and K2 value. If we look very carefully in this particular system, we still have one quantity which is, we have missed one quantity which is A. So this A value is the one which will actually determine your phase margin. Whatever the value of phase margin you will take, accordingly your things will be determined. So let us here, if you see in this one, if we take A equal to 2, from this transfer function you can calculate your phase value, and from there you can calculate this thing. So you will say that your phase margin will be somewhere nearly equal to 37 degree, or precisely it is 36.86 degrees. So this phase margin is sufficiently enough. That means my phase at omega c is 37 degree away from minus 180, because the moment it touches minus 180 we will have instability in the system. So we can say that if we keep our A equal to 2, our phase margin equal to 37 degree. Now this, how we get this phase margin? If we find out phase angle at omega c of this thing is nothing but tan inverse, this we will keep omega c here, we will get kpv by kiv minus tan inverse your omega c t delta. That is the phase we get, and from this one we know that our kp by ki is nothing but a square t delta, and if we keep our a value to be equal to 2, so that implies, so if I keep omega phi omega c is nothing but tan inverse omega c is 1 by a t delta, is a square t delta minus tan inverse omega c 1 by a t delta t delta, and this will get cancelled out. Finally we will get phi omega c at omega c is tan inverse a minus tan inverse 1 by a. So we will get this one, and from this we can calculate our phase margin, which is 180 plus 5 omega c, and if we keep our A equal to 2, that gives, and if we keep A equal to 2, we will get actually value to be equal to, phase margin to be equal to, nearly equal to 36.86 degree. So this is how we can keep either at A equal to 2 or A equal to 4, and accordingly we will get the required phase margin. So from here we can easily calculate our voltage control parameter, current controller parameters, and that's when we can design our closed loop control. So let us see how we will make our entire closed loop using this independent control method, like going into DQ model and doing ABC, and we are making IS space vector lying along the VS space vector, and since we are controlling the angle and as well as amplitude of the vector, we can say that this is also called as the vector control approach, or you can say the vector control of 3-phase AC to DC converter. Now if we have this 3-phase our inverter, this we have used MOSFET. We can also use IGBT with freewheeling diode. Here we have used MOSFET. So we have 3 half bridges, we have C, RL, L, RS. We know how we can calculate this L, C, and how we can size our switches. Then since we are actually sensing the output voltage V0 and we are sending it to our closed loop control. So we will be sensing this through voltage sensor. Through voltage sensor we are sensing, and that we are sending it through our voltage sensor transfer function to the feedback to the V0 reference, and that we will comparing, and then we go through the voltage controller. We already know how we can design the parameter of voltage controller. After that, the limit to ensure how much maximum current can be flowing in the circuit, that limit will actually define my ISD reference, and then I will be taking the ISD feedback and then having the current controller. Again we know how we can calculate our current controller parameters. I mean, if we assume it to be a conventional PI controller, then limit and then feed forward term nothing but VSD by G, and then minus minus of omega L ISQ feedback by G, and similarly in the ISQ loop, ISQ reference we are making it equal to 0. That is when we are ensuring that IS space vector is aligned along the supply voltage space vector, and that is when we can say that we are achieving balanced 3-phase operation with unity power factor current drawn from the source. And then we will have our current controller. We know how we can design our current control parameters, limit, and then finally one feed forward term to actually negate the cross coupling effect, which is omega L ISD feedback by G, that we know we have already derived in our DQ axis model. And then after this we will get our V converter D and V converter Q, and that will be sending from DQ to ABC to get our 3 modulating wave, which is we can say that VMA, VMB and VMC, and that we will actually, modulator is nothing but comparing this modulating wave with the triangular carrier going from 0 to 2 VC, and that is when we will get the required S1, S2, S3, S4, S4 gate pulses, because we will just do the comparison. If my modulating wave is greater than carrier, then top switch is on if in that phase, and if the modulating wave is smaller than the carrier, then my bottom switch is on in that phase, and that gate signal will be going to do this gating of these switches. Now if you look very carefully, we also have this feedback to be generated. This feedback, ISD feedback, is coming over here, and ISQ feedback is coming over here. While if you take ISQ feedback is coming in the cross coupling term to negate the cross coupling term, and ISD feedback is used to actually negate the cross coupling term in the Q axis model. So now if you look very carefully, so for that, how we can generate this ISQ and ISD feedback? For that, we will sense A, B, C phase current, and that through the current sensor, since we have 3 phase. So since we have 3 phase, so we are actually sensing 3 phase currents, and that is actually going to the filter, which is nothing but K1 by 1 plus ST1, and then from here we will convert ABC to DQ, and we are, while doing ABC to DQ, we will go from ABC, we will go to alpha beta, and from alpha beta we will go to DQ. And if you recall how we can do this ABC to alpha beta and DQ, we need angle theta information over here. Now this angle theta information is need to be generated. Now this angle theta information can be generated just by sensing this VAN, VBN and VCN voltages, and then we convert this ABC to DQ. ABC to DQ means first ABC to alpha beta and then alpha beta to DQ. That conversion we are doing, and while doing this DQ we are using theta, and we are using the same theta to generate my VSD and VSQ. And now since I can ensure my D axis is aligned along the voltage space vector, if I can ensure that VSQ component or the component of supply voltage space vector along the Q axis is equal to 0, that is what we are doing over here. We are giving VSQ reference equal to 0 through the controller. It could be traditional PI controller, classical PI controller you can use, and then the output of this will be nothing but the omega, because you are aligning the D axis along the voltage space vector. So basically aligning means you are changing the angular speed with which those D and Q axis is rotating, because we are making sure D and Q axis goes and get locked with the voltage space vector. So that's why we are seeing, and that we are doing by making VSQ convert 0. So from there we are also taking our feed forward term, because mostly our grid frequency, or you can say line frequency, is nearly 50 hertz. Then there will be slight variation in that frequency, so it varies around that 50 hertz. So that's why that feed forward term we have provided. Now this controller has to work to ensure that whatever the delta disturbance which is happening in the frequency, that has to be taken care of. And then after this one we will have this integration, and this integration will actually give me my theta information, because this will be my total, my actual line frequency, and that line frequency is actually this, you can say omega controller output, and this one is added with we feed forward to get the omega, which is actually getting integrated to give you theta information. And this theta information you can limit it between 0 to 2 pi, and once it crosses 2 pi you can again reset it to 0. So we can get the theta information. So theta will be actually varying, like if you see this one, it goes from 0 to 2 pi, then 0 to 2 pi, 0 to 2 pi, 0 to 2 pi, then again 0 to 2 pi, and this time period is nothing but T, which is nothing but 1 by Fs, or line frequency we have. So from here we get the theta, and that theta we will use to generate VSD and VSQ. So when we do that, and then if we make sure VSQ is equal to 0, so we are slowly aligning our D axis along supply voltage space vector, and that's when we can ensure the theta what we are getting is getting synchronized with the grid supply voltage. And that theta we use the same theta from here, we will use the same theta over here to convert that V converter D and Q value to ABC value. That's when we are ensuring that the modulating wave accordingly gets synchronized with the grid, or we can say that the supply voltage. So that is how we can ensure that we have synchronized operation, that means we have the unity power factor operation from the grid. Now this particular part is essential, this particular part from, you can say from here to the generation of theta is nothing but called as the PLL, phase locked loop. So we are ensuring that D and Q axis gets rotated and gets locked with voltage space vector, which is itself is rotating in the space with angular speed same as that of the speed with which the voltage is varying with respect to time, or you can say it is rotating with angular speed omega corresponds to the line frequency. So this is how we can get the unity power factor operation along with regulating the output voltage V naught at the desired value, and that is how we can ensure the closed loop operation of 3-phase AC to DC converter. Thank you very much for listening to this lecture patiently. We will continue our discussion going ahead, discussing about the isolated DC-AC converter in the next lecture.